Hi guys, in this video I'm going to look at the 3018 Mini CNC from Banggood. This is a small 3-axis milling or engraving machine supplied in kit form. It can mill and engrave several different types of material, which I'll be testing later in the video. This is what you get in the kit. The frame is made from 2020 aluminium extrusion, connected with corner brackets. The axes are driven by 3 NEMA 17 stepper motors, one of which is already fitted into the Z-axis carriage assembly. The stepper motors are connected to lead screws, and support is provided by rods and linear bearings. The table dimensions are 340 by 160 mm. The stepper motors are controlled by a controller PCB, which is labelled as Developer 2.0. This runs Gerbil 0.9J on an Arduino Nano clone. The clone uses a CH340 USB serial port chip, which requires a CH340 driver to be installed. Also on the controller PCB are 3 stepper motor driver carriers, which employ Heroic HR4988 stepper motor driver chips. Underneath the board are jumpers which set the microstepping resolution. There's a pin header to allow the connection of limit switches, which are not supplied, and also probe connections for height mapping. This jumper sets the mode of operation between laser and CNC. The relay on the board controls power to the spindle motor. This is simply turned on and off without any speed control. The spindle motor itself is a 775 type and it's pre-installed into the Z-axis carriage assembly. It operates on 24 volts DC, which should result in a no-load speed of approximately 7,000 RPM, but I haven't checked that. The power supply is a brick type with an IEC input. It's suitable for 110 or 240 volts input, and it has a 24 volt 4 amp output. The instructions are not very good, just some photocopied sheets, and with that in mind I've included some quite detailed build instructions in this video. To start with, I built the base frame, which is constructed from 3 360mm lengths of aluminium extrusion and 2 further 330mm lengths. These are held together with 6 right angle corner brackets and the nuts and bolts that came packaged with the brackets. The nuts being the normal hex type rather than the T-nuts that are also supplied in the kit. Protective plastic was removed from the extrusion, but there was also quite a lot of swarf in the slots, so I removed that with compressed air. The nuts and bolts were loosely installed into the corner brackets, and the frame assembled by sliding the nuts into the extrusion and tightening the joints with a screwdriver. This method worked okay, but I would recommend replacing the bolts with hex socket types as they would be much easier to tighten up with an Allen key. And I'd also use washers for all of the bolts as well. Next I built the gantry frame. This was constructed from 2 360mm lengths of aluminium extrusion, 2 220mm lengths, and the same corner brackets, nuts and bolts used for the base frame. And the measurement between the two sections should be 96mm. Returning to the base frame, I installed the support brackets for the Y-axis rails using M5 by 10mm machine screws and M5 T-nuts. The The brackets were installed 70mm in. The T-nuts are designed to rotate and engage when you turn them clockwise, but sometimes that doesn't happen and you have to resort to giving them a helping hand. You can also install the T-nuts first and screw the bracket down onto them. Next I installed the support bearing for the Y-axis lead screw using small-headed M5 10mm machine screws and T-nuts. The table bed is made up from two aluminium sections linked together with brackets. And then 4 linear bearings are loosely attached to the base. Next, the Y-axis lead screw bracket is attached to the base. The insert and spring that form the anti-backlash mechanism are inserted into the bracket, and then the lead screw is threaded through the bracket. I attached one of the stepper motors to a steel mounting plate with 4 M3 6mm machine screws. The table bed was mounted to the base frame by feeding the lead screw into the support bearing, and then feeding the 2 rails through the mounting brackets and the linear bearings. The stepper motor and bracket were attached to the back of the base frame with 2 M5 6mm machine screws and T-nuts. The stepper motor shaft and the lead screw were then joined with a coupler, and then making sure that everything was square, the lead screw bracket and the linear bearings were tightened. Finally, just checking that the mechanism operates smoothly without binding. Next, I loosely installed the X-axis rail support brackets onto the gantry frame. The top rail was then slid through the brackets and through the Z-axis carriage assembly. The top rail brackets were tightened, and then the bottom rail was also installed. The Z-axis carriage was moved to the left and the left-hand brackets tightened, and then moved to the right and the right-hand brackets tightened. The rails were then clamped in position by tightening the brackets with an Allen key. The anti-backlash nut and spring were installed on the X-axis lead screw, and this was then screwed into the threaded insert in the Z-axis carriage. A mounting plate was screwed onto the stepper motor, and then attached to the gantry frame using T-nuts and bolts. The lead screw and stepper motor shaft were connected with a blue coupler. And on the other end of the lead screw, the support bracket was installed and screwed onto the gantry frame. Corner brackets were then screwed onto the base of the gantry frame legs. Then the gantry was attached to the base frame. Two 3D printed support brackets were then installed. The supplied collet attaches to the motor shaft with a couple of grub screws, and a couple of engraving bits are supplied in the kit. The controller PCB is mounted on an acrylic plate. And then this is attached to the rear of the gantry frame with T-nuts and bolts. I added a couple of M5 washers to increase the clearance between the acrylic plate and the frame. The stepper motors can now be connected to the controller with the supplied cables. First the X-axis, then the Y-axis, and then the Z-axis. Next, the spindle motor power cable. The motor has a red dot indicating the positive side. Then the power supply and the USB cable. Moving on to the software, first we need to install a CH340 USB serial port driver. You can find it by going to the Banggood product page, following the click here link. That takes you to a Dropbox, and from there you can select the driver folder and install the CH340 driver. Next, there is a folder called Gerbil Control. This is open source software used to control the CNC machine and send G-code files to it. You can download it here, or you can also find it on GitHub. Once that's installed, we need to select the correct serial port. If you don't know which serial port to use or it's not working, then type Device Manager into search, expand the entry for ports, Common LPT, right click on the COM port, left click on Properties, then you can look at the device status, port settings and driver details. The jog key should now be working, but with reversed directions for the X-axis and Z-axis. To fix these, the direction port invert mask setting is modified to invert the pin signals for the X-axis and Z-axis. This is accomplished by sending $3 equals 5 from the console. Luckily Gerbil stores this setting and we don't have to repeat this operation each time. The jog key should now be operating correctly. To make it easier to navigate, the step size can be chosen. The 0 point for the X and Y axis is normally on the bottom left, and once this position is found, then the 0XY button is selected. To zero the Z axis, the down button is used to just touch the bit onto the surface of the material. And then the 0Z button is selected. One thing you do have to be careful about is not to drive the CNC beyond its physical range, as there are no limit switches to intervene and prevent damage. Next, we need a method of turning our designs into G-code. For that we use CAD software, and there are lots of different options, but to start with I'm using Easel from Inventables, as it's very easy to learn, free to use and runs in the browser. You just need to sign up and then access the application from the Inventables website. So let's have a go at engraving some text on a piece of wood. This is the screen that you're presented with when you start a new project. First, set the machine work area. Then the material dimensions. Set the bit type. The V-bits supplied with the kit have a 30-degree angle and 3mm width. Set custom feed rate, plunge rate, and depth per pass. The machine is not very powerful, so to start with it's a good idea to be conservative with these settings. Now let's create some text. and set the depth of cut for the text to 1mm. Let's also use one of the predefined icons. Also setting its depth to 1mm. Then we can give the project a name. Finally generating the G-code by going into Machine, Advanced, Generate G-code and Export G-code. The wood is held down with double-sided adhesive tape and the bit is moved to the bottom left-hand corner and the X, Y and Z coordinates zeroed. From Gerbil Control, the G-code file is opened and it's sent to the CNC by pressing Send. Some of the other things that I've tried are cutting 9mm plywood. This was with tabs to keep the square in place. Engraving plywood. Using a Boxmaker app to create an interlocking box pattern. Then cutting it out of a polyethylene plastic chopping board. Cutting 6mm thick acrylic sheet. Also milling a PCB, I created a simple design in Eagle, exported the resulting Gerber files to FlatCam and used FlatCam to create the G-code files. These were then opened in Gerbil Control. The copper layer on copper clad boards is quite thin, approximately 0.4 mm in depth, and the surface is usually not flat, which makes milling PCBs a bit of a challenge. To help with that, you can use a height probe where the CNC checks the height of the PCB in a grid pattern and turns it into a height map. You simply need a couple of connections from the PCB and the bit to A5 and ground on the controller. The PCB is then milled. Holes drilled. and finally the board outline is milled. This is the result. It did take me quite a few attempts to get to this point, and that turned out to be due to a faulty stepper motor on the Z-axis with excess axial play. That played havoc with the height mapping, and I didn't have a suitable replacement, so I just used an elastic band to preload the Z-axis, which worked quite well. It's also important to get the bits centered accurately, and to help with this I replaced the original brass collet with a 5mm ER11A holder and spring collet, which is much easier to use and I would say is an essential upgrade. The last thing that I tried was to mill a small face plate out of 1.2mm thick aluminium sheet. This process was quite slow, but I'm surprised how well the panel has turned out. Overall the kit has been interesting to build. It does have the potential to be a useful tool for some light duty tasks such as milling PCBs and the occasional front panel. There are a couple of areas where I want to improve the machine. Firstly, installing limit switches, as it's very easy to accidentally drive the machine beyond its range, and fitting bearings to the lead screws to transfer the axial load away from the stepper motors. This should improve the life of the motors and increase the accuracy of the machine. If you have any ideas about that, please leave a comment below. Thanks for watching and see you again next time.